Welcome to the deep dive. Today we're going to be looking at quantum computing,
Okay.
specifically with a paper by Ronit Shah called A Faster Quantum Fourier Transform.
That's good.
And basically this paper is exploring a faster way to perform something called the Quantum Fourier Transform, or QFT.
Okay.
Um, you can kind of think of this like the quantum equivalent of breaking down complex signals, like you would find in music or stock market data or things like that.
Yeah, historically there's been kind of a trade-off.
Okay.
You could either get a really accurate and exact QFT,
Okay.
but it would take a lot of steps,
Mm.
kind of like a complicated dance routine.
Okay.
Or you could get a faster one that's more approximate, but it would be less precise. And Shaw's paper is proposing a new way to structure the QFT
Okay.
that can make both the exact and the approximate versions faster.
Interesting. So faster and potentially more accurate.
Exactly.
Okay. So let's start with the basics here.
Sure.
What exactly does the quantum Fourier transform do? I know the paper describes it as taking a state in the computational basis and mapping it to a superposition where each basis state acquires phase factors related to its index.
Right.
But that's kind of technical.
It is.
How would we explain this to someone who doesn't really have a background in quantum physics?
So imagine like a symphony orchestra.
Okay.
Each instrument is playing a specific frequency,
Mm-hmm.
and all together they create this like really complex sound.
Yeah.
The QFT is kind of like taking that combined sound and separating it out
Oh,
so that you can hear each instrument's individual frequency.
got it.
It's basically helping us understand the underlying structure of a really complex signal.
So it's kind of like breaking down the components of a complex waveform.
Exactly.
Okay, cool. So Shaw's paper is proposing two algorithms, one for an exact QFT and one for an approximate QFT.
Right.
What is the core idea behind both of these algorithms?
So they both rely on kind of a divide and conquer strategy
Okay.
using a technique called recursion. So they break down the larger QFT into smaller, more manageable QFTs,
Okay.
solve those, and then combine the results. And
Interesting.
he also uses something called fast integer multiplication,
Okay.
which is a method for multiplying large numbers quickly
Mm.
to speed up that combination process.
So it's kind of like breaking down a problem into smaller chunks,
Right.
solving those chunks, and then putting it all back together.
Yeah, exactly.
Okay, cool. So how do we even measure the efficiency of these algorithms?
Sure.
The paper mentions something called gate complexity and ancilla usage.
Yes. So think of a quantum computer like a circuit
Okay.
with gates that control the flow of information.
Mm-hmm.
Gate complexity refers to the number of gates that you need to run an algorithm.
Okay.
The fewer gates, the more efficient the algorithm is.
Makes sense.
And then ancilla qubits are additional qubits that are used for temporary storage during a computation.
So they're like the scratch paper of the quantum computer.
Oh, yeah.
Okay, I got it. So Shaw's algorithms are designed to minimize both of those things.
Yes.
The gate complexity and the number of ancilla qubits needed.
Right.
What are the actual improvements that are achieved compared to the more traditional methods?
So for the approximate QFT, which historically requires a gate complexity that scales with like nlogn,
Okay.
Shaw's algorithm achieves a complexity that scales with nlogn too,
Okay.
which is significantly faster.
So it's a lot faster.
Yes.
Okay.
And then the exact QFT also sees some improvement.
Okay.
It goes from a complexity of n2 to nlogn2.
Okay.
So this means that we can perform the QFT much faster, especially for large inputs.
So as the inputs get bigger, the difference in speed is more pronounced.
Exactly.
Okay. This divide and conquer approach that's kind of recursively breaking down the QFT,
Right.
how does that actually work?
So you can think about it like sorting a deck of cards.
Okay.
Instead of sorting the entire deck at once, you can divide it into smaller piles.
Mm-hmm.
Sort those piles individually, and then just merge the sorted piles back together.
Okay.
That's the essence of divide and conquer.
Makes sense.
And it's really efficient.
Okay. There's also mention of a precomputed state,
Yes.
denoted as like KISS,
Right.
and something called the phase kickback technique.
Yes.
Can you explain what those are?
Yeah. So the precomputed state is like a tool that's prepared in advance
Okay.
that helps perform a specific operation within the algorithm. It's kind of like having a pre-made component that you can plug in to perform a specific operation.
Got it.
And then the phase kickback technique uses this pre-computed state to manipulate the quantum information, basically transferring phase from one state to another.
Okay.
It's similar to how if you strike one billiard ball, it transfers momentum to another.
Okay, that's a good analogy.
Yeah.
And then what about the Clifford plus T gate set? that's mentioned in the approximate QFT?
So those are specific types of quantum gates that are relatively easy to implement on an actual quantum computer. And they're really important in achieving that lower gate complexity in the approximate QFT.
Okay.
So it's effectively reducing the number of steps required for the computation.
So they're like more efficient building blocks.
Exactly.
Okay. And then the paper also mentions ignoring small angle rotations in the approximate QFT.
Yes.
Can you explain that concept?
Sure. So imagine you're navigating a city
Okay.
using like a GPS.
Yeah.
Minor deviations from your planned route may not actually impact your arrival time that much.
That's true.
And similarly, in the approximate QFT, ignoring these really small rotations doesn't significantly affect the final result,
Okay.
but it simplifies the calculations, which leads to a faster computation.
So they're strategically streamlining the process without really compromising on the outcome.
Exactly.
Interesting.
Yeah, it's kind of like optimizing code.
Oh, okay.
Like a skilled programmer can achieve the same output with fewer lines of code, and that makes the program run faster.
Yeah, that makes sense.
Okay.
So let's dig into the actual resource requirements on Shaw's algorithms.
Okay.
You mentioned gate complexity and ancilla usage before.
Yeah.
Can you elaborate on those a bit more specifically for both the exact and approximate QFT algorithms?
So the exact QFT algorithm that Shaw proposes achieves a gate complexity of nlogn2.
Okay.
Which is a pretty significant improvement over the traditional N2 complexity.
Yeah.
However, it does require nlogn qubits.
Mm-hmm.
The approximate QFT is even more resource efficient.
Okay.
It achieves an impressive gate complexity of nlogn2.
Wow.
And it only requires log and ancilla qubits.
Okay, so there's a bit of a trade-off there.
Right.
With the exact QFT where you have fewer gates but more ancilla qubits.
Yeah.
And the approximate QFT seems to be both faster and uses fewer ancilla qubits.
Yeah, that's right.
Okay. So the approximate QFT sounds like a good choice if you don't need a really high degree of precision.
Yeah, for a lot of applications, that's perfectly fine.
Right. Okay. So the paper also kind of dives deeper into this divide and conquer approach of breaking down the QFT.
Right.
Can you walk us through how that actually works in practice?
So let's use that card sorting analogy again.
Okay.
Imagine you have a large deck of cards that you want to sort.
Right.
You could try to sort the entire deck at once.
Yeah.
But that would be a pretty daunting task.
It would be.
So instead, you can divide the deck into smaller piles, sort those piles individually,
Right.
and then just merge those sorted piles back together.
Yeah.
So that's the divide and conquer strategy.
That makes a lot of sense.
And it really simplifies the sorting process.
And it's the same idea with the QFT.
Yeah, exactly.
Where you're breaking it down into these smaller, more manageable QFTs.
Right.
And then combining the results at the end.
Exactly.
Okay, cool. And so how does fast integer multiplication fit into this divide and conquer strategy?
Right. So after you perform the QFTs on those smaller groups of qubits,
Right.
you need to combine the results to get the final QFT for the whole system. And this combination process involves calculations that can be significantly sped up using fast integer multiplication.
So that's where that comes in.
Exactly.
Okay. And we touched upon the pre-computed state T before.
Yes.
And the phase kickback technique. Can you give us a little more detail about how those elements actually work within the algorithm?
So you can think of the pre-compute state as a specialized tool.
Okay.
It's designed for a specific task within the algorithm, like having this pre-made component that you can just plug in to perform a specific operation.
Got it.
And then the phase kickback technique is how we actually utilize that pre-computed state to manipulate the quantum information. So it's a way to transfer phase from one quantum state to another.
Right.
Kind of like how if you strike one billiard ball, it transfers momentum to another.
Right. That's a good way to think about it.
Yeah.
So the pre-computed state is kind of like this shortcut, and the phase kickback technique is how we use that shortcut to manipulate information.
Exactly.
Okay, cool. And then we talked about the Clifford plus T gate set, which is used in the approximate QFT.
Right.
Could you explain why those specific gates are relevant?
So those gates are important because they're relatively easy to implement physically on a quantum computer. So by using this specific set of gates, Shaw's algorithm reduces the overall complexity of the approximate QFT.
Okay.
And that leads to faster computation times.
So they're more efficient building blocks, basically.
Exactly.
Okay. And then finally, let's revisit this concept of ignoring small angle rotations in the approximate QFT.
Okay.
You mentioned before it's kind of like taking a slightly different route on your GPS without really impacting your arrival time.
Right.
Can you elaborate a bit more on why it's okay to ignore these small rotations and how that actually contributes to the speed up?
Sure. So in the approximate QFT, we're not really looking for the exact solution, right? We're okay with something that's close enough. In these small angle rotations, they really only have a very tiny effect on that final outcome.
Okay.
So by ignoring them, we can really simplify the calculations and get to a faster computation without giving up too much accuracy.
Right.
You can almost think of it like rounding numbers.
Yeah.
Sometimes a close approximation is good enough.
Yeah, right. Right. Gets you in the ballpark.
Yeah, exactly.
Okay. So this research is really fascinating, I think.
Yeah.
It gives us a glimpse into this
It does.
a complex world of quantum algorithms.
It does.
And the constant work that's going on to try and make them faster and more efficient.
Yeah, it's really exciting.
What stood out to you most in Shaw's work here?
I think the most interesting part was the way he uses that divide and conquer approach, combined with all those techniques like fast integer multiplication and the pre-computed state.
Right.
It really shows how creative problem solving can be applied to make these quantum algorithms better.
It's like thinking outside the box.
Totally.
Okay. So the paper ends with a few open questions.
It does.
One of those questions asks whether these techniques can be applied to input sizes that aren't powers of 2.
Yes.
Can you talk about that a bit more?
So a lot of the math behind the QFT and these algorithms works really well when the input size, like the number of qubits, is a power of 2.
Okay.
But real-world problems, they don't always fit into those neat little constraints.
That's true.
So figuring out how to adapt these techniques to handle different input sizes is going to be crucial if we want to make them useful.
It's like the next step.
Exactly.
Okay, well, this has been a fascinating look into Ronit Shah's research.
It had it.
I really appreciate you taking the time to break it all down for us.
Of course, happy to be here.
This is The Deep Dive. We'll catch you next time.
Sounds good.